Thank you for listening. This is a joint work with Nick Freeman. What we wanted to study was coalescing random walks and their limit to stable webs. Imagine that we have one worker starting from every side in the lattice, set to even. For each xn in set to even, an independent arrow is drawn from xn to either x minus 1 n plus 1 or to x plus 1 n plus 1 with probability 1/2. Then our walkers will move around along the arrows. And we will have walkers that coalesce once they meet. For example, if we start with these 2 points, then we will have some random walk started from here until here, and the other one will start from this point until they meet, they coalesce, and they, after this point, they move as just one simple run. A natural problem is to find the scaling limit if space and time are scaled by epsilon and epsilon squared. Discrete paths along arrows are random walks, as this pink one. Then, the continuous paths are Brownian motions. The problem is that there are Brownian motions that start at every point in R2. So the solution or the scaling limit is the so-called Brownian web. Fontes et al. Characterizes it as a compact set of continuous paths such that for each set in R2, there exists a unique path P set in W, and any finite deterministic set of points, set 1 and up to set K, the collection P set 1, P set K is distributed as coalescing Brownian motions. With NIC, we have 3 goals. First, we wanted to study an extension that allows the possibility of CADLAC paths. Then, we want to characterize tightness for random sets of these CADLAC paths, and we want to discuss tightness for coalescing random walks approximation to webs made of alpha-stable Levy processes. And for this one, we show that there is a failure in tightness. So let me start with the set of CADLAC paths. We denote by P the set of CADLAC paths in R2, and we are going to associate a CADLAC path in the sphere. This is using the following space-time transformation. For any point xt, we are going to map it to hyperbolic tangent of x over 1 plus t and hyperbolic tangent of t, as you can see in the picture. Something important to notice is that the coordinate axes are inverted in the sense that the time it is in the vertical line and the space is in the horizontal line. For each f in P, we are going to denote by sigma f the first time where f is defined. We are going to use the SKOROHOD metric in the sphere. Then, for any 2 CADLAC paths in the sphere G and H, with a starting point sigma G and sigma H, we are going to define lambda GH, the set of strictly increasing bijections from sigma G1 to sigma h1 such that the following supremum is finite. The value of this supremum we are going to denote it by norm of lambda. Then G is a complete separable space under the following metric. In the metric, we can notice that it is important to know the distance between the initial points where the function G and H are defined, and we are going to take the infimum over all the possible strictly increasing bijections of the norm of lambda and the supremum over all the t in sigma g1 of the absolute value of g of t minus h of lambda t. With this metric in hand and the previous space-time transformation, we can have a metric for our space of CADLAC paths. So we are going to denote it by D. Moreover, we can denote by Kp the space of compact subsets of PD, and we are going to associate the Hausdorff metric. This, the Kp with dk, is going to be our state space. And observe that it is a complete separable metric space. In order to study tightness, we need to restrict the CADLAC paths in R2 to bounded sets. In other words, let denote by ALT the following box, and for any CADLAC path F, we are going to define the restriction of F to ALT by FLT, as you can see in the picture. Then, with Nick, what we proved was that a sequence Xn of random elements of Kp is tight if and only if the following limit goes to 0 or is 0, where F double prime and B double prime and B plus is defined as these two supremum. Observe that these two supremum are the analogous of modulus of continuity, and actually they have the following interpretation. For B double prime, we can say that CADLAC path's tightness fails if, in the limit, the sequence Xn contains two jumps occurring arbitrarily close together, neither of which vanishes in the limit. While B plus tells us that tightness fails if, in the limit, there are big jumps arbitrarily close to the starting times. Then, as an application, we show that a system of coalescing random walkers making suitable heavy tail jumps will fail to be tight in Kp under the space-time scaling limit that will correspond to a single random walker converging to an alpha stable process. And the reason behind this was the presence of too many particles that at once resulted in at least one of them making a large or big movement too soon after its own starting time. And therefore, because what I explained before, tightness fails. And thank you so much. These are some of our references. This is our paper, and you can see the definition and the characterization of Brownian. Thank you very much.